Worksheet problem 18.2 asks us to rank the following compounds in order of lowest to highest boiling point, denoting the compound with the lowest boiling point as 1. So we're trying to rank boiling points here. Whenever a problem asks me about a certain phase change, I kind of like just get myself oriented. So the boiling point is when we're going from the liquid phase to the gas phase. It requires energy. You're going from a less energetic state to a more energetic state. And you also have to break apart molecules from each other. And what I mean by that is that if you have a liquid here and you have your molecules packed in relatively tightly, what you're going to do is add energy until they look more like a gas. We have to move these molecules away from each other in order for them to go from the liquid phase to the gas phase, which is where intermolecular forces come in. If the molecules are held more tightly together by their intermolecular forces, then it's harder to pull them apart. Here is a ranking of the 3 main intermolecular forces that we talk about. We see that hydrogen bonding is the strongest intermolecular force. Then there's dipole-dipole interactions, and then London dispersion forces is our weakest force. What we can gather from all this is that something that has the strongest intermolecular forces holds the molecules together tightly, and as a result, it's harder to go from the liquid phase to the gas phase. So what this tells us is that the one with the lowest boiling point will have the weakest intermolecular forces, and the one with the highest boiling point will have the strongest intermolecular forces. So we can start off here looking at F2. This is a diatomic gas, nonpolar, because there's no difference in electronegativity between the 2 fluorines. The only intermolecular force we see here is London dispersion forces. Looking at CCl4, it's a tetrahedral molecule. There are no lone pairs on the carbon, and everything bound to the carbon is the same molecule. These dipoles that are coming along the bonds, pulling electron density away from the carbon to the chlorine, is uniform, so this is an overall nonpolar molecule. As a result, the only intermolecular forces it has are London dispersion forces. CF4 will look very similar. We just exchanged one halogen out for another, so we'll have all 4 fluorines bound to the carbon in a tetrahedral geometry. As we just saw before, all these fluorines pull electron density away from the carbon to the same magnitude. They cancel out, and this also ends up being a nonpolar molecule. This also only has London dispersion forces. CH4, we are just swapping out those halogens for hydrogens now. Carbon's actually going to be a little bit more electronegative, so we'll see a slight pull of electron density into the central carbon, but it's still to the same effect, where this molecule will be nonpolar, giving us only London dispersion forces. So now that we've determined what intermolecular forces are at play in each of these 4 molecules, we have to rank them in some way. And usually it's easier to rank them when they are different kinds of intermolecular forces, but there's also a difference between the strength within London dispersion forces. And so the way to differentiate between what molecules have the strongest London dispersion forces actually comes down to size. Bigger molecules will have larger London dispersion forces. When I say bigger, I mean by mass. So what we can do here is just compare the masses of each of these 4 molecules and then determine that way which one has the strongest intermolecular force. Between F2, CCl4, CF4, and CH4, we have the following masses: 38 grams per mole, 153.82 grams per mole, 88 grams per mole, 16.04 grams per mole. And so now we can compare these. We see that methane, or CH4, is the smallest at 16 grams per mole. F2 is the next smallest at 38 grams per mole, followed by CF4, and then CCl4. So we had said that if something has less intermolecular forces, then it's easier to break apart, and then therefore has a lower boiling point. Well, CH4 is the lightest. Lighter things have less London dispersion forces, and so CH4 will be what I assign as having the lowest boiling point, followed by F2, then CF4, and lastly, CCl4.